In this research paper titled, Energy-Based Reward Models for Robust Language Model Alignment, authors Anamika Lakib and Ruki Zhang from Purdue University explore ways to improve how large language models, or LLMs, align with human preferences. LLMs are powerful AI systems that generate text, but they need guidance to ensure their outputs match what humans find helpful, safe, and ethical. This process often relies on something called reward models, which act as judges to score how well a response fits human likes. Reward models are a key part of a technique known as reinforcement learning from human feedback, or RLHF. This method has three main stages. First, supervised fine-tuning, where the model learns from examples. Second, building the reward model using data annotated by humans. And third, optimizing the model through methods like best-of-n sampling or proximal policy optimization. The reward model essentially takes a prompt and a response, processes them through the LLM's architecture, and outputs a single scalar score to indicate quality. However, standard reward models have limitations. They struggle to capture the nuances of complex human preferences, such as subtle ethical considerations or context-dependent judgments. They also don't generalize well to new, unseen data, meaning they might perform poorly outside their training scenarios. Additionally, during reinforcement learning, these models can lead to issues like reward over-optimization, where the LLM learns to exploit flaws in the reward system to get high scores on responses that aren't actually aligned with human values. To tackle these challenges, the authors introduce a new framework called the Energy-Based Reward Model, or EBRM. This is a lightweight, post-hoc refinement approach that doesn't require retraining the original reward model, making it efficient and easy to apply to existing systems. Instead of just outputting a fixed scalar score, EBRM models the entire distribution of possible reward scores. This means it treats rewards as probabilistic, capturing uncertainty in human preferences and helping to filter out noisy or incorrect annotations. Let me break this down. In a standard reward model, you feed in a prompt-response pair, get an embedding, a vector representation, and then map that to a single reward value. EBRM builds on this by adding an energy-based model on top. Energy-based models are a type of neural network that learns to assign low energy, or high probability, to desirable outcomes and high energy to undesirable ones. So, EBRM uses the embeddings from the pre-trained reward model and models the conditional distribution of rewards given those embeddings. At inference time, it refines the reward by iteratively optimizing it to maximize the energy function, effectively selecting the most plausible reward score. The authors outline several key techniques for training EBRM. First, they use conflict-aware data filtering. This involves analyzing the training data for inconsistencies, like when multiple annotators disagree on a response's quality, and filtering out or downweighting those examples to reduce noise. Second, they employ label noise-aware contrastive training. This method trains the model to distinguish between positive and negative examples while being robust to errors in the labels, using contrastive learning to pull similar, high-quality pairs closer in the reward space and push apart low-quality ones. Third, they incorporate hybrid initialization, which combines pre-trained weights from the original reward model with new parameters for the energy-based component. This ensures that EBRM starts from a strong foundation without needing to train everything from scratch. Overall, these strategies make EBRM adaptable across different models and tasks, and it's designed to be computationally efficient since it doesn't involve retraining the base reward model. The paper includes empirical evaluations to demonstrate EBRM's effectiveness. They tested it on standard reward model benchmarks and found significant improvements in robustness and generalization. For instance, in safety-critical alignment tasks, EBRM achieved up to a 5.97% improvement over traditional reward models. This means it does a better job at handling scenarios where responses could be harmful or misleading. Furthermore, the authors conducted reinforcement learning experiments to see how EBRM performs in real-world alignment pipelines. They found that using refined rewards from EBRM enhances the overall alignment quality of LLMs. Specifically, it helps delay reward hacking, a problem where models learn to game the system for high scores without truly improving. By modeling reward uncertainty, EBRM prevents the model from over-relying on flawed signals, leading to more reliable and human-aligned outputs. One of the strengths of this approach is its scalability. Unlike other methods that require training multiple models or ensembles, which can be resource-intensive, EBRM acts as a plug-and-play enhancement. You can apply it to any pre-trained reward model without major modifications. The paper also mentions that the code for EBRM is publicly available, encouraging further experimentation and adoption. To visualize this, imagine the standard reward model as a simple judge that gives a yes or no score. EBRM is like upgrading that judge to a more thoughtful evaluator who considers a range of possibilities, weighs the evidence, and delivers a more accurate verdict. This is illustrated in Figure 1 of the paper, which shows the standard ERM outputting a scalar reward from an embedding, while EBRM adds an energy-based layer to refine that reward by optimizing it iteratively. In summary of the contributions, the authors have developed EBRM as a framework that boosts reward model robustness and generalization by explicitly modeling reward distributions. It uses innovative training techniques like conflict-aware filtering and noise-aware contrastive learning, all without retraining, making it a practical tool for enhancing existing alignment pipelines. These advancements address key pain points in LLM alignment and pave the way for more reliable AI systems.